Alright, so here our aim is to make sure that we're able to represent a linear distributed load as we did for uniform distributed, and then write the equation appropriately to make sure that it acts only on a particular part and not on the entire beam, right? So then this is what we do. We are revising. We know that the basic units of the discontinuity function is of this form, where we have plus or minus magnitude of the load, right? We have this x minus a Macaulay bracket, and then we have n depending on the load applied, right? So now let's deal with the one on the left, and then let's write a wall the load equation and then see what we are going to do, right? So for this particular one, if we are writing everything out, so let's see, let's put the reactional loads there, the reactional forces, so of this form, right? Yeah, okay, yeah, right. So let's see. So if we are writing out the load equation, this is how it will be, right? So we have a w of x, right? This is our origin, so if we are starting from here, we are moving in this way. The first load that we meet, we have two loads actually, two. So we have this support, and then we have the start of the uniform distributed, right? So if you're writing this out, the support goes up, right? So that's plus, and then you have a y. We just represent because we don't know the actual value for it. We've not found it, that's why. So and then we have x minus a. Sorry, the a should be a value, right? The a is where it starts. Where does it start? It's just the position of it. It's just at the origin. So 0, Macaulay bracket. What's the n? It's a point load, right? So that's minus 1, right? The next one is that at that same point we have the distributed load, which is pointing down, right? So that's a minus. That's a minus. And then what's the magnitude? The magnitude is this w here, because that's the highest point here. Okay, then again, one thing for the what's the name, the linear distributed load is that usually, you see, when we wrote this, we said mp w and then k, right? Well, we are saying this is a linear uniform distributed, and then this is a linear distributed, right? But then most of the times we use the w to represent just the maximum height of it, right? And saying that this w is just at this point here. This is the same as this 30. This 30 is representing just this point, not just the entire side, saying as a key, not a key, but just this side. Are you okay? And then because we are saying it's a linear distributed, there's a slope, right? So in order to write the magnitude, so let's say we have the direction now, right? We have the direction. In order to write the magnitude, this is how I write. It's basically a slope, right? So change in y over change in x, right? So the y is this, which is basically the load, right? So w, so the is w here, right? Minus 0, all on what? The x, right? The x is this side, right? This way ends, right? So L minus what? W, right? So that's how it is, basically. That's how it is. So we end up with what? Just W and L. But you should always remember that it's actually a slope, right? So we have the direction magnitude now, Macaulay bracket. X, where does it start? It starts at 0, right? And it's a linearly distributed, right? So that makes it 1. Are you okay? Though you are seeing some W here, we've already explained why so, right? So that's how it's written for this one. And then if you write it this way for this particular one, it makes sense. Why? Because when you turn on this particular linear distributed load at 0, it goes on up to the very end of the beam, right? So it makes sense if you leave it this way. There's no turn on or turn off or anything. When you turn it on once, that's it. It acts on the entire beam, right? So now we are going to do same or similar for the linear distributed load that acts on a particular portion of the beam, right? So let's see. Let's go ahead and do that. Before we do that, come on. Okay. It's very crucial that we know the difference. And then most of the times you just, for the linear distributed, you just see this W here. At times you even specify that it's actually, what's the name, give this here to show that it's actually some kind of height or something, this w here. But at times you just see a value or just a w or whatever, and then they just put it here, showing that it's just for this height here. That's what I'm saying. So we should take note, right? Okay, so now we're going to do same for the linear distributed that acts on just a portion of the beam. Okay, so we are done with this, right? We're trying to do for the one on the right hand side. The one on the right hand side. Okay, so then looking at this one, we are still starting from the origin, which is right here. So the load equation w, right, of x, right, the first load we encounter is this 25 just at the origin, right? So it's down, so negative. The magnitude is what, 25, right? And then let's write this out. 25 Macaulay bracket x, where does it start? At the origin, 0, right? And it's a point load, so that's -1, right? So we move on. The next thing we encounter is what, the uniform distributed load. That's just where it starts, right? So we have a, it's going down, so we have a minus, right? The magnitude is 30 Macaulay bracket x minus what, 1, right? It's a linearly distributed load, so that makes it 1, right? Now we move on. What's the next thing we encounter? Okay, now it's clear. The next thing we encounter, in fact we don't encounter anything till we get to this side. We'll come back to this one, but it's very safe if you actually write. Now that you even understand this whole thing, it's actually safe to continue and write the counter straight forward. So let's see. Let's write out the counter. So the counter will be of this form. What happens is that for this one, for this linear distributor, it has slightly different representation, but then we are going to do the sketch to understand what's actually happening. So let's take it down a bit. Let's see. So the actual thing is this way, right? Now from here to about here, and then this, right? Slightly different, but I understand it's still the same thing. And then we have our beam, a straight line. Okay. Our beam, right? And now what happens is that so the beam is up to here. So let's do this well. So it's clear. Okay. What is happening is that if we use this equation with the one we've written, if we use this, it's 30, right? So it's 30. Okay. If we use this, what it's saying is that it starts at 1 and it doesn't end. It actually gets to the very end. So let's use red to see what's happening there. So what the equation I've written here and the one underlined with red, that's what it means. It starts so it gets to the end of the beam like this, right? But that's not so, right? So then what does it mean? We actually need a counter. But this one, the slight difference is that it has division within that side, because we can't represent this. Let's see. So the counter will be exactly this way. So this, the same magnitude, and it comes down, right? And it's this way, right? So it's like this, opposite direction, right? But then there is no way that we can represent this directly, right? It doesn't look like either uniform or what you call a linear distributed, right? So what we do here is that we actually divide this to get a uniform distributed and a linearly distributed. So this is what happens. So let's see. Let's do the division. So somewhere about here, when you do the division here, it turns into, we have two portions. Well, we have the linear distributed here, and then we have the, what's the name, uniform distributed just down, right? So we actually need two equations to represent the counter, right? So we'll do that, and then we'll actually get to know what's happening. Are we okay? Yeah. So let's do this. In order to represent that, okay, so now let's just write the counter for before we even get to the D, right? Because now we understand the whole concept. This down. Okay. So now we need a counter, right? Let's bring it up a bit. So now we need a counter. And the counter, we know it to be in two parts. Let's use green. Yeah. Two parts. The first part is, let's write the uniform distributed first, right? Writing now is actually up, so that's a plus. The magnitude is what? Just 30, right? And then there's something we missed, right? What was it? If you notice from this first one, we actually did W magnitude, right? Acting on the whole length, right? Which is a slope. So if you are doing same here, if you are doing same for this particular one, the 30 is acting on a specific portion, which is 3, right? Yeah. So that's how it should be. And then for the counter, we have the linear, the uniform distributed portion. So let's do that. 30, right? Macaulay bracket. Direction is up, 30 magnitude. Macaulay bracket. X minus what? Where does it start? It starts here, but the origin is about here, right? So that's 2 plus 3. That gives us what? 4, right? Minus 4, and it's a what? The first counter is this one, right? It's a uniformly distributed, right? So that's 0. The next counter, which is also up, right? The same direction, up, plus, right? What's the magnitude? 30. But it's what? Linear, and it's acting on a portion, right? Which you know to be just this 2 here, right? It's acting just the side, so it's about here. Let's see. So the counter is about here, right? So here, and it's like this, right? It's acting on just that side. So that's 2, right? Let me clean this. Right? Macaulay bracket x minus y. It also starts at just the 4 respect to the origin, right? And it's a linearly distributed, right? And if it's linear, that makes it 1. Right, so that's it. So you are done with the counter. Now we go back and then write for the rest. So we started from here, we go here, we wrote the start for this, which is this yellow one here, linearly distributed, and we go here, right? We are writing the counter, which is all this in the green here, right? And after that, we move on, and when we get here, when we get to the very end there, what we need, when we get to the very end here, the only thing that is here is the reaction, the dy, right? So that will be, is up, the reaction is up, right? So that will be plus dy, so direction, magnitude, right? Macaulay bracket x minus what does it start? Oh, here, right? So that's 5 plus 2, that makes it 7, right? And it's a point load, right? So that's minus 1. So that's it. That's the representation. That's the turn on and off of a linear distributed load, right? All right. Confirm that.